dielectric breakdown, and sparks. Air is a very good electrical dielectric. And remember, that's also the same thing as saying insulator. However, any dielectric can be electrically broken down. Which means the dielectric has now become a conductor. This is what you need to try to understand. We're going to ask the question that reads as follows. Under what conditions can a dielectric become a conductor? And that's what we're going to explore now. When this happens, this is called dielectric breakdown. So what we want to do is that we want to figure out how do we cause dielectric breakdown. And typically the way we see this in classrooms is what's called a Van de Graaff generator. So to cause dielectric breakdown, one typically, there's other ways to do this, but one typically, at least in a classroom, uses a Van de Graaff generator, which I will typically just call the Van de Graaff. So a Van de Graaff uses a complicated process, but effectively uses charging by contact between two dielectrics at the bottom and transfer charge via a rubber belt to a metal sphere. So picture-wise, this is what I want you to think about. I have the ground, and we're going to set a Van de Graaff on this, and it has a base, And so when I'm thinking about this base here, it has a rod. It's typically a clear rod. And this clear rod, excuse me, it's a cylinder, not a rod. And what you're going to find here is that there's a belt inside. So what you're seeing here is that there's a belt that rotates up and down by a small motor. So down here at the bottom, you're finding that in here, there's a small motor that causes a belt to rotate. And so then up here at the top, we have this metal sphere. So again, this guy is a conductor. And then right here, we have our rubber belt. That carries charge up. And in some way here, it's going to deposit charge onto there. Now, what you're going to find here is that there's a second system. And this is what we call a discharging sphere. So in this situation, we also have a rod here. And then this guy is connected all the way to the ground. So this is a discharging rod or sphere. And then this whole thing here is the Van de Graaff. And just one last thing here is that this here is an insulator, and so is that. So now what happens is that we're going to put particles, air particles in between. So what I'm saying here is that we're going to have air particles, and they're in between these guys. And we'll find here that we have a mixture of air particles. So right here, we have a mixture of N2 and O2 air particles. So that's the setup of the Van de Graaff here. So when the Van de Graaff is turned on, we've already said that charges from the bottom go up and get transferred to the sphere. So typically, when the Van de Graaff is turned on, negative charges are transferred to the sphere above. So if I'm transferring negative charges, then it's going to become negatively charged. Now, the discharging sphere is brought nearby to the Van de Graaff. which induces charge on it. So picture-wise, I'm going to try to, I have this already, so I'm just going to copy and modify this just to be quicker. So if I look at this thing, here's what I'm seeing. So when we transfer charge, it has to be from high energy to low energy. So let's get rid of all of this stuff here. So now what's going on here is that I have this type of thing. So what ends up happening is that now I'm going to develop a very strong negative charge on the Van der Graaf. And as a consequence, the discharging sphere develops an induced positive charge by pushing negative charges as far away as possible. And the reason why we have that ground, what ends up happening is that these negative charges now start to move to the ground. So what it does is as it pushes electrons, so electrons are pushed down towards the ground. And as a result here, I'm getting positive charges on the side closest to this. So now, here's what we know. The ground here is the low potential energy, electrical potential energy. This guy over here is a high potential energy. So now I have a charge difference. I have an energy difference, and now I can do work on the air molecules. So here's what we're seeing. So in effective picture, shows that on this side, I have my Van der Graaf. And what I know about the Van der Graaf is on the surface, it develops a negative charge. So this is the Van der Graaf. And then on this side, I have my discharging sphere. And that develops a positive charge. And this is the discharging sphere. So in between here is these air molecules, right? So here, right in here, I have all those air molecules. So now if I look at the electric field between these two goes in this direction like that. So here's what happens. As more and more charge builds up on the Van der Graaf. Remember what I said? That's the Van der Graaf sphere. The electric field reaches a critical dielectric breakdown value. And this is what the value is. So then E breakdown can be written numerous ways, but the most common way is that it is 3 million volts per meter. Or I can write this through centimeters. And if I write it through centimeters, it's the same as 30,000 volts per centimeter. I don't need, and by the way, I can write this for millimeters too, right? I can make this, I can also write this as 3,000 volts per millimeter. There's multiple ways to write that, and they're useful in their own form here. So this is what's important. When the field strength reaches, excuse me, this critical value, air undergoes dielectric breakdown and is now an electric conductor. So the question is, how does this happen? So this is how air becomes a conductor here. This E breakdown will do work and change the kinetic energy of loose electrons. These electrons are accelerated such that a collision with an air molecule remember, when I say air molecule, N2O2, but it turns out that we're really talking about N2. That's what that value, O2 actually has a lower value. So a collision with an air molecule will knock out an electron from the molecule. This causes a chain reaction. Now, I got to be careful about this chain reaction word because it has nothing to do with nuclear radiation, but it causes a chain reaction that results in an electric current. In other words, it allows charge to move. So here's the way I see it here. So I have a starter electron, and we'll get into more details here of how we get a starter electron. But this guy is what I call the starter. And you could see here that this value is just, it starts off at 1 electron. Now what I want to do here is that I want to look at the air molecules. Let's say that this is my air molecule, and this is N2. So this electron now gets accelerated and it collides with the N2. As a result, that electron that came in is now moving down. Let's say it's just moving, it's really moving in the forward direction. And so I retain the same electron. But now, in the other direction, I now have a second electron that has now been knocked out. So this guy right here is the knocked out electron. And so then we start the process. So what does the process says here? So now I have other air molecules. And so then this guy hits here, this guy hits here. And so what happens? I now get a repeat of this process. In other words, I'm going to get another electron here, and I'm going to get another electron here. And then these are new electrons. So what you're seeing here is that I am producing more electrons. So I started with 1, I now have 2, I now have 4 electrons. My starter plus 3 initial ones. Then the process continues. So then I come over here and I go like, yep, here's more air molecules. And then the collision continues. And the reason why it continues is that we said we reached this critical value. That's the breakdown value, where these electrons are accelerated in the direction opposite of the electric field. So then you can see here is that now I'm going to get essentially the same type of thing. So literally in a flash of a second, I'm getting a lot more electrons. In other words, I'm getting a flow of charge. So if this is I believe this should be 8, I now have jumped to 8 electrons. Now you could see how the process starts to move here. So then I have more air molecules, and then I get 16, 32, 64, 128. It just keeps going, and it happens very, 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 very quickly. But the bottom line is this. What this means here is that now I have current. I am moving electrical charge. So what I'm seeing here is that there is a transfer of charge through a dielectric material. So that means here is that the dielectric is now a conductor. That's what we mean by dielectric breakdown. This whole process means that. And so what's really interesting about this is that dielectric breakdown they always say that if you see dielectric breakdown, that The reason is that you see sparks. So the dielectric breakdown of excuse me, the dielectric breakdown is, how do I say this? Occurs when a dielectric becomes a conductor. This is the most important aspect. It's the primary thing. A secondary effect occurs. When charged ions like N2 plus and O2 plus recapture a loose electron, they emit light. That we see as a spark. So if you see a spark, it's a secondary effect. The primary effect is that the dielectric becomes a conductor. The secondary effect is that a spark occurs when these charged air ions recapture an electron. So there's a really, really good video. Okay, really good video. And all of these videos that I share with you are on the class webpage. Okay, so I want to come and share with you this video that I'm talking about. This is an MIT group that does the demos for that, and this is a good one. Okay, and you'll see here is that this guy is a gigantic Van de Graaff. I mean, enormous. I've only seen a few in my lifetime this big, but check this out. There you go. That is the Van de Graaff, one of the most impressive machines in Physics 4B. Really, really impressive. But that's the reason why you get that spark. So remember, go watch the video. And this is called the dielectric breakdown of air. There's another minute of the video that does other things, and we should come back later to talk about that, which I will. But for right now, all we needed to do was talk about this. Now, there's a couple of things that I want to look at here, and I want to say that I want to come back to look at the Van de Graaff again. So what happens here is that now, suppose we have an isolated Van de Graaff. And what that means here is that there's no grounding sphere or grounding rod. So suppose we have an isolated Van de Graaff and it reaches E breakdown. If one tries to increase the field's strength above E breakdown, breakdown occurs and reduces the field's strength. So what do I mean by that? So again, let's do our Van de Graaff. So if I'm looking at my Van de Graaff, right, here's my ground. And then I have this thing here. And you know what? I'm going to move this down because I'm going to need it. So now what happens is that I've now reached my critical value. So I get this value of E dielectric breakdown. And we know that that's 3 million volts per meter, but in our case, we would typically think in the language of centimeters. So a better one to think about is 30,000 volts per centimeter. So that's a more appropriate value. So now what happens? If I get to here, what am I actually doing here? The language, again, can be really slippery here. So what I'm seeing here is that now, even though there's no discharging sphere, I do have nearby air molecules. So let's say that I have these air molecules. And what ends up happening is that I am accelerating the electrons and I'm knocking electrons out. But if I'm knocking electrons out, note that these air molecules are now positive. And the Van de Graaff is quite high, and it has a very, very strong electric field. So what's it going to do to these positive charges? You guessed it. It's going to accelerate these guys towards the Van de Graaff. So all of a sudden, when you get dielectric breakdown, the positive air molecules are attracted to the Van de Graaff, and when they hit the Van de Graaff, they reduce the charge. So let's write that down. When dielectric breakdown occurs, electrons are accelerated and knock out electrons from N2O2 molecules. This creates positive ions that are attracted and collide with the Van de Graaff. This causes a reduction of charge and reduces the electric field of the Van de Graaff. In other words, that now, if I have the breakdown value, if I get to that, then that's really the maximum value. But as soon as charge starts positive charge starts interacting with the Van de Graaff, this now falls below the value for the Van de Graaff. So what has to happen? More charge has to be put up in order to increase this thing to the dielectric breakdown. It's the language issue that I want to talk about. The common language is the Van de Graaff is leaking charge off. And this is the cause of the reduction in charge. It's not leaking. It's because it's accelerating the electrons, and then they go and attach to the Van de Graaff, reducing the charge. So, but that's besides the point. So one can never have a Van de Graaff field strength above E breakdown. Which is the maximum value. Possible maximum value possible in air. Again, we could talk about other things other than air later when we have more experience, but we'll save that for another chapter. So I wanted to show you another video that's really worth looking at. And what you're going to find here is that we have a YouTube video By the way, these are all YouTube videos. And this is a woman. By the way, it's not that she's a woman. I could also say that I know of men that do the same thing. So this is a woman or man at a gas pump. And I want you to watch this video because I think it's worth looking at. So let me go up here. And this is what we want to. And so here's the video. So I'm going to start it here. And here we go. The quality is very poor and there's no sound. Now here's the important piece right here. She turns on the pump and then look what she does next. She gets back in the car. What happens when she gets back in the car? You have the seats, you have the pants, they're both insulators, they're rubbing. In other words, charging by contact occurs. She is now charged. Some people think that that woman was stupid by doing what she did. I think she was very smart. Pumps, I mean, we're not going to get into that discussion. So let's go highlight and what just happened here. Let me make sure I'm sharing my window. I am. Okay. So one of the things that you want to think about here is why. So the first thing that says, what happened with the woman? So let's just sort of like highlights here. So what we know here is that the woman gets back into her car. Now what we have here is that we have charging by contact and she gets electrically charged. Two, as she moves towards the conducting, in other words, metal handle of the gas pump, her charged fingers induce charge. So what do I mean by that? I could imagine, let's pick one finger, but she has fingers. It's not just one finger. So I have a finger, right? So here's her finger. And let's say she is negatively charged now. And then I look at the handle of the gas pump, and it is a metal handle. So now we are inducing charge onto that handle, right? So right here, we're going to say that this is the gas pump handle. And so now what we're seeing here is that in between here, we have a mixture, right? So in here, we have a mixture of air, gasoline, and electrons. And it's the starter electron that we're most worried about, because now I have created an electric field, right? I have an electric field. And according to Coulomb's law, we know that that field is proportional to 1 over r squared. So what's happening? As she gets closer and closer and closer, her voltage or her electric field is growing in strength. And then all I need is 1 electron. And this is my starter electron. And then that starter electron then experiences an electric force that then starts the dielectric breakdown value. So once that dielectric breakdown value occurs, what happens? You got the chain reaction, air becomes the conductor, and as a consequence, a spark is created. So then if I come here to 2, 3 here, as her finger gets really close, E breakdown is reached. So now the dielectric breakdown process starts. As a consequence, a spark is created that ignites the gasoline particles, causing a fire. That's not a problem. If you want to get back into a car, that's not a problem. What you want to do here is that you are now charged. When you get out of your car, before you approach the gasoline pump, by the way, it's really hard to actually do this, but take your hand and touch the metal part of your car. Then you'll discharge, and that won't happen anymore. So I just have one small thing left that I want to do here. And I want to ask a question that's a common question that some people believe can happen. And here's what the question is. Can an external electric force or electric field get strong enough to ionize an electron from an atom? And in this case, I'm really thinking hydrogen because it's easier to think about. Now, when I say the word ionize, I really mean, can we rip out the single electron? That's what I mean by ionize. The answer? No way. Not even close. So let's do a very rough calculation to show you what I mean here. So this is going to be a rough calculation to show why this is not possible. So the first thing that we have is that we typically treat hydrogen with the proton binding the electron. So if I look at hydrogen, here's what we typically see. We see here that we have a proton charge, and at some distance, we're going to have some electron. And one ground state level is that it's 1/10 of a nanometer, the distance between them. So when I look at this, there is a field produced by the proton. We want to calculate what that proton field is. So remember, this is a very rough thing, because in an atom, you got to ask the question, why isn't the electron moving towards the hydrogen atom? Or, excuse me, the hydrogen nucleus, the proton? Why is it just stationary out there? You can't answer that question. You need quantum mechanics to answer that question. So this is a very rough calculation. So a rough calculation shows the strength of the proton electric field where the electron is at. So when I look at this thing, I'm going to say that here's the electric field of the proton, and we know that this is 4 pi epsilon, and it's going to be the distance to the edge of the atom times q of the proton. And so when I look at this, I'm just going to approximate this. So 1 over 4 pi epsilon, that's about 10 to the 10. The charge of a proton is about 10 to the minus 19 coulombs. And then this guy's about 10 to the minus 10 squared. So when I calculate this thing, roughly, this is 10 to the 30 minus 19. So I'm going to get a value of an electric field of about 10 to the 11 newtons per coulomb. So once again, in order to overcome the proton's electric field, one needs a minimum of a field. So then I need this minimum strength of about 10 to the 11 newtons per coulomb. Right? That is a big ass value. That is just gigantic. So in other words, if I want to rip out an electron from hydrogen, right? Once again, so this is the value needed to rip the electron from the proton. But there's a problem. This is impossible to achieve since the maximum value of E field in air is the breakdown value of E breakdown of 3 times 10 to the 6 volts per meter. Therefore, to ionize an electron from an atom requires a different process. And that's why we talk about kinetic energy.